So the year before COVID, 2019, there was a polar FRQ on number 2 with calculator. So let's break this thing down. There are some interesting parts at the end of this, and then we'll talk a little bit quickly at the end and why I think you should kind of review these polars. All right. So they're giving me S. This isn't 2 curves. Sometimes they give me 2 curves. Sometimes they give me 1. All right. So let S be the region enclosed by this polar equation. And they're even nice. They're telling me it's from 0 to square root of pi to where it's going to keep closing itself down. But again, I think it's important, and I always tell my students, if you really want to get good at polar, you just kind of understand how it's being built. And then once you understand how it's being built, it makes it a lot easier to do the calculus behind, or the calculus to the actual questions itself. So there's my curve. They're squaring my theta in my sine. That's why you see that square root of pi. But let's talk right now. So at the initial ray of 0, if you plug in 0, 3 times 0 is 0. Sine of 0 is 0, so it starts at 0. Now, the terminal ray is root pi. So when I plug that in, right, I get 3 times the square root of pi. But this becomes sine of square root of pi quantity squared. Sine of pi is 0. That's why this goes back to 0. So it's closing itself down from 0 to square root of pi rads. Again, this is with calculator. I don't need to dig too much deeper than that. All right, find the area of S. And again, this is calculator, so a polar always is going to, probably not always, but almost always, is going to ask you to find its area, if there is going to be one on the AP exam. Remember, it's just half the integral from alpha to beta of the radius squared. So really what you're doing is you're accumulating. You're starting at the initial ray, which is 0, spinning it to the square root of pi rads, and you're just filling in the radius squared. You're using the integral to accumulate that as you're swinging around the rays, or the ray. So hopefully that kind of explains it a little bit to you. But we want to take half the integral from 0 to square root of pi. And again, this is calculator. I don't need to write all of what the exact function is. It's just r theta. The AP grader knows what you're doing if you write that. But we need to calculate this. And again, if you already know how to do this kind of stuff, you can kind of forward through a little bit faster and get to pieces maybe you need to see. So 1 over 2 times the integral from 0, be careful, to root pi. And just plug this in a parenthesis, and we're going to square it. So that's 3 square root of x. I always use x. Now be careful, this is the flaw again. Sometimes on the Inspire, it doesn't recognize 2 functions being multiplied if you don't put the multiply between them. So let me back that up. So times sine of x squared. Always make sure you're in rads. The x, forgot to square that. So that's half alpha to beta radius squared. Again, my fat fingers strike again. Hit enter. I don't want the exact answer. I want the 3.534. Pretty simple stuff in my mind. All right, what is the average distance? Remember, the distance is just the radius, right? From 0 to square root of pi. So that's just the average value of a function. Fundamentally, you know it's 1 over b minus a. In this case, beta minus alpha. All times the integral from alpha to beta of your radius. Let that accumulate itself. All right, so 1 all over square root of pi minus 0 is just square root of pi, all times the integral from 0 to square root of pi of your, and I'll show this, r theta, and it's just minus 0. Remember, I mean, it's already it's built from the pole, if you understand how polars being used or built. All right, let's do this. Control divide. 1 over square root of pi times the integral from 0 to square root of pi of my r. And I guess I could go up and copy this just in case I need it. Well, I'm not going to do it right now. I'll just plug it in again and I'll copy it right now. This would be, what, 3 square root of x times, and I'm pretty good about copying stuff. I should have copied my r just so I can keep pasting it in and making my life easier. And then sine of x squared dx. Again, I'm going to go into here and I'm going to hit shift and I'm just going to copy this just in case I need it again. So that'll be control C. I'll just hit enter. And that gives me 1.580 for this integral. So that's the average distance from the origin to the point from 0 to square root of pi. Now here's where it got a little weird. All right, there is a line through the origin with a positive slope that divides the region S into 2 regions with equal areas. Write but do not evaluate an equation involving one or more integrals whose solution gives the value of m. All right, here's my thought. I want to cut this in half, right? I'm not going to bring my array all the way up. All right. So this is my theta from here to here. This is my y component. This is my x component. And this is my r. Right? So my slope would be y over x. My tangent of theta would equal that y divided by my x. Right? So that would be my slope. And again, you had to start thinking, like, how in the world do I get this back to rectangular where I have a change in y over my change in x? I would have gone up in here and drawn the situation. Now, if you solve for this theta value, you would just take the inverse tan of the slope m. Right? Instead of y over x, we're just substituting the m in, because they need me to write an interval that gives the value of m, right? So I need to divide that into 2 equal areas. What a twist this was. And there's even another one coming in a second. So the first thing I would need is I would need the area, or half of the area of the entire closed S, right? So I would take half of half, remember it's half integral from alpha to beta of the radius squared, which would go from 0 to root pi. But this would just be of what? R theta quantity squared d theta. So that would be half the area, right? Now, this is where this was tough. Like, you now want to figure out the area to this m value. So you want to find m this way. You're going to take half the integral from 0 to inverse tan of m. Nice little twist there, right? Of the r theta squared, quantity squared, d theta. Again, I didn't look at the number breakdown of this, but I wonder how students figured that one out. I would have at least put this, this, and this, and realizing that I had to somehow make my m in my upper limit here. And I bet a lot of students just put m up there. You needed to figure out changing y over changing x. You needed to somehow get that slope figured out from the situation up here. All right, last piece of the puzzle. For k greater than 0, let a of k be the area of the portion of region S that is also inside the circle of r is equal to k cosine theta. All right. So we need to understand something about, like, let's say we have r is equal to 3 cosine theta. And I'm just going to do this off on the side. If you go back to the, I believe the 2017, they had this type on there too. It seems to be a type they like. So let's figure this out from 0 to pi over 2. So at 0, you get 3. At pi over 2, it goes back to 0. And then it's just gonna be the half circle. This is that half circle scenario from 0 to pi over 2, right? It's kind of shifting things over. So this automatically is only going to go from 0 to pi over 2 and shut down in this form. I mean, you could do r is equal to 4 cosine theta, 5 cosine theta. But as k goes to infinity, right, this thing should kind of shut this part down, right? This should be inside of it only from 0 to pi over 2. So again, a lot of students would struggle with this. So as k approaches infinity, the circle r equals k cosine of theta grows to enclose all points to the right of the y-axis. So by explaining that, the limit as k approaches infinity for that area of that enclosure just has to be 1/2 the integral from 0 to pi over 2, because it's, again, we got to understand how that one's built, of the r theta quantity squared d theta. Now, I have that somewhere in my calculation. I just need to change my upper limit, right? So I'm going to grab this, and I just need to change my upper limit to pi over 2. Hit enter, control enter. And I get 3.324. So it has to approach that. Again, I don't know how students would have done with that one. But knowledge is power. Seeing these type of things can help you if they throw curveballs at you moving forward. So again, who knows if they're going to give you a polar FRQ in the version or the year that you're studying for, but why not see all the different types of polars they've thrown also out. Hopefully this helps. Good luck.